Greetings, class! Have you ever wondered why a skydiver jumping from a plane doesn't just keep accelerating until they literally break the speed of light? Today, we will study dynamics of non-uniform motion and resistive forces. I'm absolutely thrilled to guide you through this explainer. We're going to master exactly how forces behave in the real world and figure out why literally nothing moves quite as simply as it seems on paper. So let's jump right in.
Okay, so let's kick things off by defining exactly what we mean when motion isn't perfectly constant. You know, in our theoretical textbooks, we're always calculating these perfect scenarios with constant acceleration. But out in the real world, non-uniform motion is the standard. It's motion where acceleration actually changes with time. And why does it change? Because of resistive forces. We're talking friction, air resistance, fluid resistance. These are the invisible interactions constantly messing with an object's acceleration as it moves. We almost never see pure, constant acceleration because our environment is just packed with matter, pushing back against us. Let's unpack these forces, starting with the one you're probably most familiar with.
Right, let's lay down the basic ground rules for friction. Friction is basically that super stubborn force acting between two surfaces that are touching. And the golden rule here is that it always acts opposite to the direction of motion. Always. Say you're pulling a heavy book forward across your desk. Friction is that annoying force pulling it right backward. Now, the texture of the objects matters a ton here. Rough surfaces kind of interlock at a microscopic level, and that produces way greater friction. Smooth surfaces, they produce less. A perfectly smooth surface, which, by the way, is a total theoretical ideal, it doesn't really exist, would produce exactly zero friction. So if your pulling force is greater than the friction, boom, the book accelerates. But if you pull with exactly the same amount of force as the friction, those forces balance out perfectly and the book just cruises along at a constant velocity.
So, the absolute crucial takeaway here is that friction isn't just an annoyance, it's an everyday necessity, and it perfectly sets up Newton's second law for us. Think about it. Walking will be a completely impossible, hilarious disaster of slipping around without friction. Every single time you take a step, you're heavily relying on the friction between your shoe and the floor. Car tires desperately needed to brake safely or grip the road when turning. But, you know, it's definitely a double-edged sword. Excessive friction causes heat, wear and tear, and major energy loss in machines, literally throwing away useful kinetic energy and turning it into useless thermal heat. Which leads us right to force dynamics. The actual motion of an object completely depends on the resultant force acting on it. According to Newton's second law, force equals mass times acceleration, or F equals ma. That super simple yet profoundly important equation is the cornerstone of literally everything we're doing in this explainer.
Here are the core details regarding this topic. Review them intently for their deemed crucial for your finals.
Let's make this resultant force concept super concrete by looking at three specific scenarios of pulling a heavy box. Okay, case 1. You pull a heavy box harder than the friction is pushing back. Your resultant force is forward, so you guessed it, the box accelerates. Case 2. You pull the box exactly as hard as the friction pushing back. The resultant force is now 0. Now, you don't instantly stop. Actually, you just keep moving forward at a constant velocity. Case 3. You get a bit tired and your pulling force drops below the force of friction. Now, your resultant force is actually acting backward against your movement, causing the object to slow down or decelerate. See? It's a perfectly logical system when you break it down.
Okay, imagine trying to swim in a pool filled with regular water versus a pool filled with, thick glue. That brilliantly illustrates exactly how viscosity impacts drag. When objects move through fluids, and hey, a quick reminder, in physics, a fluid can be a gas like the air around us, or a liquid like water or oil. They face a resistive force called drag, or viscous force. So what is viscosity? It's really just a measure of a fluid's internal resistance to flow. Water has a relatively low viscosity, so you glide right through it. Engine oil has a much higher viscosity, making it thicker and tougher to move through. And that pull of glue? Insanely high viscosity. The simple rule of thumb is this: the higher the viscosity of the fluid, the much larger the drag forces opposing your motion.
These are the vital facts linked to this section. Study them thoroughly as they are vital for examination point of view.
Moving on to the air right around us, let's connect the drag a cyclist feels to the very first moments of our skydiver's fall. Air resistance is simply drag in a gas, and you literally feel it every day. Crucially, the faster you move, the harder the air pushes back against you. That's exactly why you see Olympic cyclists hunched so far forward over their handlebars. They are actively trying to reduce their cross-sectional surface area to minimize that drag. So let's apply this back to a skydiver jumping out of a plane. This actually answers our hook from the beginning. A falling object doesn't just accelerate forever. In that very first millisecond of the fall, their initial velocity is zero, which means the air resistance is exactly zero. At that exact split second, only gravity, their downward weight, is acting on them.
Now, this exact sequence is absolutely vital for understanding terminal velocity. Picture a falling skydiver again. Initially, their resultant force is at its absolute maximum, pulling them straight down, so their acceleration equals g, or gravity. But as their speed rapidly increases, they start crashing into more and more air molecules. This causes the upward air resistance to increase. As that upward drag gets bigger and bigger, the overall downward resultant force shrinks, which means their acceleration decreases too. Now, they're still falling and they're still speeding up, just less rapidly. Eventually, and this is the absolute magic moment, that upward air resistance perfectly equals their downward weight. The resultant force becomes exactly zero. Acceleration completely drops to zero. The skydiver locks into a constant maximum speed. And that right there, that is your terminal velocity. The absolute key condition to memorize for your exams is this: resultant force equals zero and velocity is constant.
Parachutists usually reach terminal velocity well before hitting the ground, which is a good thing because the alternative makes for a pretty terrible afternoon. This whole scenario brilliantly illustrates how we can actually manipulate these forces. So you're falling at terminal velocity, your forces are perfectly balanced. Then you pull the cord and deploy the parachute. Suddenly, your surface area massively increases. Because of that, the upward air resistance just skyrockets. It's suddenly way, way larger than your downward weight. Since the resultant force is now acting upwards, your speed decreases rapidly. You heavily decelerate until once again the forces balance out. The air resistance drops as you slow down until it perfectly matches your weight again, giving you a new, much lower, and totally safe terminal velocity for landing.
Okay, let's shift gears from the air to
Key vocabulary related to this topic is displayed, sorted according to multiple exam boards. These words require serious attention during preparation because of their importance and must never be neglected. In addition, analysis of past paper is provided for each exam board and paper style. Focus on this carefully as it will greatly assist in improving your preparation. Try to understand the context and practical use of each keyword rather than learning them by heart alone. Frequent practice with these terms in past questions will enhance your accuracy and overall performance.
Please subscribe our channel to get more educational videos. Thank you.